Hello everyone, welcome to TLE Eliminators PCD for Codeforces Round 1050 Division 4. How was the contest, guys? It's been the first Div 4 in a long time, I think, right? Let's see. Hi, hello. Did till E, did till D. F was easy, but less time. Yeah, I think someone else will do lead code by weekly, Suraj. It might be uploaded in a few hours. Mm, F was doable, yes. Yeah, Codeforces was being a bit annoying today. Like it wasn't opening right now as well. Okay. Alright then let's get right into the PCD. I see most people have solved like up to D ish at least. Right? Anyone who didn't solve up to D? Anyone who solved maybe only AB or only ABC here? We won't spend much time on the starting problems then. Um, okay. So before we get started, as usual, I'd like to inform you that Eliminators helps self-paced courses for competitive programming, which are available at really affordable prices. Just um, a couple of thousand rupees, which is really affordable if you see what exactly the level of content being taught, right? And although yeah, obviously for CP and almost any other thing you can obviously find online resources for them, then why is our course special, right? Why should you take our course? And the reason is simple. A lot of times in your CP journey you get stuck, you feel directionless, you don't know whether what you're studying is the correct thing you're studying, or whether you're doing enough problems or enough novel problems. And that's why our course is perfect, because it's handpicked and curated by experienced competitive programmers who have gone through the same journey. So we have chosen all the correct, like, important topics, right? So for example, if you're a coder who can solve, let's say, two problems in div 2, then we know that these are the probably topics you need to focus on to be able to solve three problems, like binary search, two pointers, number theory, combinatorics. And those topics are taught. Each topic has recorded lectures as well as detailed solutions and problems. So yeah, and there are hints and video solutions for all the problems, progress tracking leaderboard, as well as doubt support available almost throughout the day, right? So when you have a specific doubt at a problem and you want to talk to someone else about it, let's say, and you don't really have any friend to talk to, then obviously you can just ask a question, and then within 10 minutes max, a mentor will pick that question and he will solve it for you. He'll explain what is wrong in your approach. So yeah, for this, all these benefits, definitely do check out the telemeters course. Yeah. Okay, so let's get started with the problems, right? Okay. So problem A, Sublime Sequence. Farmer John has an integer x. He creates a sequence of length n by alternating integers x and minus x. He asks you to find the sum of all integers in the sequence, and x and n go up to 10. Okay, and it's given in the input x and n. All right. So let's go ahead and write down a sequence. Problem A. So a given sequence will look something like this. So let's say x, minus x, plus x, minus x. So let's say n was equal to 5, then there would be a plus x, right? So we can obviously see that this x and this x are getting cancelled, this x and this x are getting cancelled. So our final answer is simply x. What if it was n equals 6? In that case, it would be something like this: x minus x plus x minus x plus x minus x. And in this case, all the x would get cancelled, right? All the x would get cancelled, and the answer would be 0. So it is pretty easy and obvious to observe that the final answer depends on the parity of n, right? It depends on parity of n. What does parity mean? It means it depends on whether n is even or odd, right? So if n is odd, if n is odd, then sum of the sequence is equal to n is equal to x, and if n is even, then sum of the sequence will be equal to 0. Since it's alternating plus and minus, then sum of sequence will be equal to 0, right? And that's all for this question. We can simply code that up, right? So let's have a look at the code here. For each test case, we input x and n. If n is odd, so n% 2, we can see out x, otherwise we see out 0. So that's all for problem A. The time complexity of this will be big O of 1, right? Big O of 1 to find the answer per test case. Okay, so we can move on to problem B now, right? Problem B, lasers. So there is a 2D coordinate plane which ranges from 0 0 to xy. Okay, so 2D coordinate plane which ranges from 0 0 to xy. Let's just full screen this, right? Okay, problem B. Problem B. So let me just draw the 2D coordinate plane. So let's say it ranges from 0 0 to xy, right? So 0 0, and let's call this as xy, right? And let's just draw these grid points of the coordinate plane, right? So like these are the points on your coordinate plane, right? So yeah, these are some points on your coordinate plane, right? And it ranges from 0 0 to xy. You are located at 0 0 and you want to head to xy, so you are located here, you want to reach here. There are m vertical lasers with the ith laser spanning bi0 to biy, right? So vertical lasers are there. So you have lasers like, let's say this is bi0 to biy, so this is one laser and this is another vertical laser. And then you have n horizontal lasers as well, spanning 0 ai to xai. For example, you have a horizontal laser like this, and another horizontal laser like this, and maybe another horizontal laser like this. Now you can move in any direction, but your movement must be a continuous curve. Okay, your movement must be a continuous curve. So you can't teleport like this, but you can do any curve in this boundary, like this curve or this curve and so on, right? And you need to count the crossings. So what is a crossing? A crossing is, if you cross a boundary, then this is one crossing, right? If your path is crossing a boundary, then it's a crossing. If it crosses two boundaries at the same time, let's say if you have intersection between two lasers, then this will count as a two crossings, right? It won't count as one crossing, it will count as two crossings itself. Fine. So they have shown this. What is the minimum number of crossings possible to reach x comma y? Okay, what is the minimum number of crossings possible to reach x comma y? And now the input is given nmxy. Each laser's position is given for horizontal laser as well as vertical laser. Nm goes up to 10 to the power 5. Now the observation here is pretty simple. No matter what you do, observation, and this should be pretty simple intuition if you think about it a bit, how curves work and how lines work. No matter how you move, how you move, you move, you will always touch, you will always touch each line, because see, the line is basically a barrier. Like this blue line, no matter where we go, we are going from 0 to xy, right? So no matter what, we are going to at least cross over it once, right? At least we are going to cross over it once, at least once, at least once. And we don't need to touch a line more than once. We don't need to come back down again, right? We can just keep going, right? So intuitively, if you draw it out and see, it's very simple. Obviously a mathematical proof will take time, but we don't need to write a mathematical proof. We can just see this through pure intuition, right? And it doesn't help to go through the intersection, because this will count as two crossings anyways, right? This will count as two crossings anyways. So that's why no matter what wiggly woggly shape you make, you can always find a path like this, and you can just always just take the direct path as well. So basically the answer will always be, answer is always n plus m. So the number of crossings, number of horizontal plus vertical crossings, that is going to be the answer, and that's what you can print to the output. Let's have a look at the code. um, we take in nmxy, and we can take in the input. The input doesn't really matter, so I'm just storing it wherever in a temporary variable, and then printing out n plus m. Okay, so the answer is simply n plus m, and the time complexity for this is big O of n plus m to take input, but the answer itself takes big O of 1, right? So big O of n plus m for input, but the answer itself is just big O of 1. Answer is big O of 1. Okay, so that's it for this question. I hope there are no doubts for A and B, right? Can I move on? So Saad, Rafi, I think you had a doubt on B. So does this clear it up for you? And Himanshu, how did you do sliding window on this? I do not see why sliding window was needed. It just needed the observation that no matter what you do, you're gonna cross all the lines, and that's the solution for B. Okay, so should we move on to C now? Let's move on to the problem C. Um, okay, problem C, pacer. Okay, problem C. Farmer John is running the fitness gram pacer test. He takes 1 minute to run to the other side of the gym. Therefore, at each start minute, he can choose to either run to the other side or stay in one place. Okay, so there are two sides of the gym. So side 0 and side 1, and then he can either run to the other side or stay in his same place. It takes 1 minute for that. If he chooses to run to the other side, he gains 1 point. Okay, so basically there is a gym, and this gym has side 0 and side 1. Okay, side 0 and side 1, and there's farmer John over here. Okay, this farmer John, and then in 1 minute he can run from one side to one other side, and this gives him a point of one exactly, and it takes 1 minute. Okay, so basically he can run between these two sides, or he can wait some time and then he can run, so that's also valid. Now he's going to do the pacer test, and basically what the pacer test does is it happens n times, it plays audio 10 times. At the start of the AIth minute, he must be at the BIth side of the gym. Okay, so basically, at the start of the AI minute, he must be at the BI side of the gym, and this should be guaranteed. Okay, so the question says that at some minute, like let's say minute 2, at minute 2, he should be in side 0, and at minute 4, he should be at side 1. He should be at side 1, and then at minute 7, he should be at side 1 again, and let's say at minute 9 he should be at side 0. So let's say these are the rules of the pacer, something like this, right? What is the maximum number of points farmer John can acquire while ensuring that he meets the requirements of this audio? Okay, so that's what we need to find. N and M goes up to n goes up to 10 power 5, M goes up to 10 power 9. What is M? M is the total number of minutes, right? AI is the minute of the audio, so this is AI values, right? And AI is in ascending order, so AI is greater than AI minus 1, and BI is either 0 or 1 because that's the side, right? Side has to be either 0 side or 1 side. Okay, right. So okay, so how do we solve this problem? um yeah, so what we can observe is that while ensuring that, let's say we start at side 0, right? We start at side 0. So while ensuring that farmer John starts at side 0, and basically what we care is simply at the previous time where his side was fixed to the current time, how many runs could he have made, right? So for example, if he started at side 0, Then at minute 2 he has to be side 0. That means he can make one run like this, right? He can make one run like this. So he gets total 2 points, right? He can make two runs to that side and come back, and he can get 2 points. Now at minute 4 he needs to be at side 1, so he makes a run over here, but now he cannot move again because he needs to stay for minute 4, right? He needs to stay for minute 4. So this is minute 3, 2 and 1. Okay. uh yeah, so this is 4, right? Now at minute 7 he needs to be side 1 again. So let's say he does a run. So this is 5, this is 6, and then for 7 he needs to stay again, so he stays for 7. Now for 9 he needs to be on 0, so he can run, and on 8 he'll reach here, and on 9 he'll have to be 0. Now let's say M was till 10, so that means he can still make another run and reach till here. So that's the basic idea. Basically we need to make as many runs as possible. So this is going to be our intuition. Make as many runs as possible in the given time. Okay, in the given time. So, and how do we find this? So the duration where we can make the runs, we can write like this: duration equals current time, which is a of I, minus the previous time. Okay, so minus the previous time, which you can write as a of I minus 1, or for now let's just call it the previous time. Okay, so this is the duration where we can run, and then we need to know whether the side has changed or not, right? So current side versus previous side also we should know. Current side equal to previous side. This also is a relevant value to our answer. Okay, so now if the current side has changed from the previous side, that means that we have done odd number of runs. That means we have done an odd number of runs. So basically we simply need the largest odd number less than the duration, right? Less than equal to the duration. Okay, so if the current side is not equal to the previous side, um so let's write this as case 1 current side is not equal to previous side, right? So in this duration we can make the largest odd number less than equal to duration number of runs. Okay, now in the case 2, current side is equal to previous side, current side is equal to previous side. So now in this case we can make the largest even number of runs. Okay, so because we need to come back to the original position, so we can make maybe 2 runs, or maybe we can make 4 runs, maybe we can make 6 runs, so on, right? So the largest even number we can make um less than the current duration which we have, right? So largest even less than the duration, right? So once we calculate this, we can simply do answer plus equal to largest even, and in this other case we can do answer plus equal to largest odd, right? And finally when we have processed all the runs, then we can simply print the answer. Print answer. Okay, so the time complexity of this will simply be big O of n. Let's have a quick look at the code for this in case this is not that clear maybe. So let's have a look at the code. So initially we take in n and m as input. So n is the number of fixed points which we have in the audio. M is the total time which we have for the running. The previous value is 0. Why is previous value 0? Because that's the initial starting time. And since we're starting at side 0, the starting position is 0. Also, the number of points is going to be 0 because initially the number of points we gained is going to be 0. So this is going to be our answer. Okay, we take input xy. So xy is simply at this minute you need to be at this side. So if the current side is equal to previous side, right? If the current side is equal to previous side, then we are on the case 2, right? This is what it means. If y equals to position, That means we are on the case 2, current side is equal to previous side. So now we need the largest even number less than the duration. Duration equals to current time minus previous time. So duration is simply x minus previous, right? That is the duration. We need the largest even less than this. So we can write this as x minus previous subtracted by x minus previous mod 2. And if it's an odd number, this will make it an even number. If it's an even number, it will stay as it is, right? Similarly, for the other case where current side is not equal to previous side, so we can write this as current side equal to previous, current side not equal to previous, right? And in this case, we need to simply take the smallest, take the largest odd number less than the duration, right? Largest odd number less than the duration, and it's the same idea. Simply x minus previous, and instead of subtracting this mod 2, subtract 1 minus this mod 2, right? So this gives us the largest odd number less than equal to the duration, and we add that to our points. At the end, for the m remaining minutes, we can do as many runs as possible. So we simply do m minus previous. All right, and finally we print the final value of number of points. Okay, so that's all for this question. It was mostly just implementation again, um, and yeah, that's about it. Any doubts? Any doubts regarding this? You can put odd even checks, yes, and obviously you can do it that way, just to simplify the code and make it into a clever one liner. That's why I wrote like this. If you want, you can make odd even subcase for both of these cases. So this is for Lakshay Narula. D and C should have been swapped. Really? I don't know much. I found them okay order, but all right. Okay, should we move on to problem D, or should I explain C more? Please tell in the chat. Yeah, you can make subcases like that as well. Yeah, so essentially that's the same answer, Manas. The same thing, but you wrote a case. I put it in the formula. Any way you implement, obviously the answer remains the same as long as you implement correctly. Okay, so let's move on to problem D. Destruction of the Dandelion fields. So Farmer John has lawnmower turned off initially. He has n fields. Each has a of I dandelions. He can visit in any order. He will visit each field exactly once. Right, so that's it bold. Each field will be visited exactly once. His lawnmower has a mind of its own. Before visiting each field, it checks if it has an odd or even number of dandelions. If it has an odd number, then the lawnmower toggles its state. Otherwise, if it's an even, nothing happens. And if the lawnmower is on, it will cut all the dandelions. Otherwise, if it's off, then the farmer John will simply visit the field and cut no dandelions. Okay. If he visits the fields in optimal order, what is the maximum total number of dandelions he can cut? Okay. So what is the maximum of dandelions he can cut? Um, let's see. N goes up to 10 power 5 again. So big of n log n solutions will work. And sum of test cases will not exceed 10 power 5. And they've given some examples, right? So now here we know that odd and even is important. So let's just make a test case with a bunch of odds and a bunch of evens. Okay. Problem D. So let's say our input is something like this: 2, 4, 6, 8, and then let's say some odd numbers: 1, 3, 5, 7. Okay. So now initially the lawnmower is off. So it's best if we visit the odd one. Okay. Best if we visit an odd one. So let's say we visited this one, or maybe we visited this one. Now our lawnmower gets turned on, and our answer becomes 7, right? And now the lawnmower is on. So since your lawnmower is on, it's best if we visit all the even ones, right? It's best if we visit all the even ones now, and then we can come back and finish the odd ones off, right? So then we can visit all the even ones and nothing changes, the lawnmower still remains on. Now that we have done the first odd and we have done all the evens, now we can go to some other odd number, the lawnmower will turn off. Then we go to some other, it turns on, and then it turns off again, right? So on, off, on, off. So in this kind of pattern, the answer would be 7 plus 2 plus 4 plus 6 plus 8 plus 3, correct? And so this is our example one. Okay, so we observed some things over here. Now let's take another example. In this example, there's only even numbers. Let's say 2, 4, 6, 8. Now in this case, the lawnmower will never turn on. Never turn on. Right, so no matter what we visit, all our even numbers never turns on, the answer will be 0. Okay. So basically, we have made one observation immediately. Observation 1, if no odd numbers, then answer is 0. Okay. Observation 2, observation 2, if at least one odd number is there, if at least one odd number is there, is present, then all the even positions can be added. All the even values can be added. Can be added. Right? So this is what we have observed. Right. Now, what about the odd positions, right? So for odd positions, observe, let's take an example with all odds. So let's say we have all odd number of dandelions, 1, 3, 5, 7, 9. Okay. So the first field we visit, that will be on. The second field we visit, that will be off. Third field which we visit, that will be on again, off, and on again, right? So from this, what we can observe is, we can observe for the odd number ones, for the odd numbered elements, let's say there are total n number of these. Okay, let's say there are total n, or let's say total m number of these, m number, m in number. Then we can be on for, see, we cannot revisit them, right? So we can be on, we can be on for exactly n by 2 of these. Okay, n by 2, like ceiling of n by 2 of these. Okay, so we can choose any n by 2 of them, any ceiling of n by 2 of them, and be on for those. So which ones should we choose to maximize the answer? Final observation. So to maximize the answer, maximize the answer, simply choose largest n by 2 odd numbers, right? So we can sort and we can find the largest n by 2 odd numbers, sort them, then find. Okay, so that's all for this question. If there is no odd number, it's 0. If there's at least one odd number, then all the even ones we can be adding. If there are n odd numbers, then n by 2 of them, or half of them, we can add, and in that half we will choose the largest possible values, so we can sort and choose the second half, right? So let me do a full example. So let me do a full example. Let's say our array was something like 2, 4, 6, 8, 1, 2, 1, 3, 5, 7, 9. Okay, so in this case, there is at least one odd number, so all the evens will be added to our answer, right? Our answer will be, all the evens will be added. Now in the odd numbers, there are total 5 odd numbers, so we will choose ceiling of 5 by 2, which is 3, right? 3 numbers we can choose, and we will choose the largest 3 odd numbers. So here the largest 3 are 5, 7, and 9. So plus 5 plus 7 plus 9, and this will be our answer, right? So the time complexity to find this answer will be big of n log n, obviously, because of the sorting, right? Big of n log n for sorting. Let's have a quick look at the code for this. So we can input n. Our initial answer is 0. We make a vector for odd numbers. We input x. If x is odd, we push it into the odd numbers. Otherwise, we add it to the answer. Okay, the even numbers we're just adding to the answer. If odd is empty, so if there's odd dot size is equal to 0, that's what I've written here. If odd is empty, our answer is 0. We can print 0 and we can continue. Otherwise, we will sort the odd numbers and then let m be the odd number size, right? So from m by 2 till m, we can sum all the values. So we're summing all the second half of these odd numbers, right? If the odd numbers are sorted, we will sum the second half of this sorted values, and then we can print the final answer. And that's it for this question, right? um, any doubts in this? Any doubts in this, or should we move on? Any doubts in this, or should we move on from this? Big of n log n is the time complexity because we're sorting the odd and next values, right? Okay, then I think we should move on to problem E. Right. Problem E, split. Farmer John has an array A containing n positive integers and an integer k. Let A of L and R be subarray. So it's a normal definition of subarray, right? The sub array from L to R. And he performs the following procedure to independently determine if the subarray is awesome. Initially, Farmer John has k empty multisets numbered from 1 to k. Then for each element in A, if it is in the subarray, then he places it in multiset 1. Otherwise, he places A of I into any multiset he wants, which may or may not be multiset 1. Okay. Subarray is awesome if there is some way for him to place elements such that for every value v, all multisets contain the same number of elements with value v. Okay. So he wants to make all multisets contain the exact same elements. We have to output the number of awesome subarrays. Okay. So let me give an example because this definition might be a bit complicated. So let's say uh, problem E. Let's say our number of multisets is equal to 3, and our initial array, let's say it is 5 4 2 2 4 5 um, 5 4 2 2 2 2. Okay, so this is our initial array. Now basically when we choose a subarray, let's say we chose this subarray, is this subarray good or not? Or is this subarray awesome or not? How do we find that? We have three multisets, right? We have three multisets, and the values of this subarray have been forced into multiset 1. Okay, the values of this subarray have been forced into multiset 1. So this is multiset 1, multiset 2, and multiset 3. Okay, multiset 3. Now we have to make it such that each value appears exactly the same amount of times in each multiset. So what we can do is we can insert into any other multiset for the remaining elements. Okay, the remaining elements we can insert into any other multiset. So for example, to make each have at least one 5, we can take this 5 and insert it into multiset 2, take this 5 and insert it to multiset 3. So we get 1 5 over here, 1 5 over here. Similarly 4 and 4, 1 4 over here, 1 4 over here. What about 2? We can take 1 2 and another 2 and put it here. Now these three remaining 2s are there. We can distribute one here, as well as one here. And now we made all the multisets equal, right? And each frequency is also equal. So that is the goal, and that's why we can say that this one is awesome, right? This is awesome. Now, what about a subarray, a different subarray? Let's take a different subarray and see whether it works. Okay, so let's take a subarray like this. We just draw three multisets. Right. So let's say this multiset has been having 2, 4, 5, 5, because each value of the subarray has to be added to the multiset 1. Now we have to make the others also have the same values or equal values. So now there's only 1 5 remaining in the array, right? Only 1 5 is remaining in the array. So if we put it here, um, there is no 5 here, and there should be 2 5s here, right? Because there are 2 5s over here. That means 2 5 should be here as well. But there are not enough 5s for this problem, right? There are not enough 5s to satisfy this problem. So that's why this is not an awesome subarray. Okay, right. So I hope this much is clear. Um, so what have we observed here so far? So one direct observation we can make, which I hope is not very controversial, right? This should be a direct observation. Frequency of every value. So frequency of every value for all values v should be divisible, should be divisible by k. Okay, so for the entire vector, for all the values in the vector, its frequency should be divisible by k. And the reason for this is simple. The reason is that otherwise it's impossible to split into three multisets, right? So if this is not true, then the answer will be 0. If this is false, simply print 0 and continue to next test case. Okay, so this is your first observation. And second observation is each multiset, observation 2, right? What did we observe? We observed that each multiset, since it needs an equal number of values, um, since 5 has a frequency of 3, 5 has a frequency of 3, it appears one time in each of them. Okay, it appears one time in each of them. Similarly, 4 has a frequency of 3, so it appears also one time in each of them. 2 has a frequency of 6, so it appears twice in each of them, right? 2 comma 2, 2 comma 2, 2 comma 2. If 2 appeared 3 times, it would not be possible, right? So each value appears frequency of value divided by k times in each multiset, in each multiset in the optimal, in the optimal slash awesome case, right? Awesome case, right? So is that much clear, guys? Yeah, it should have a frequency divisible by k, and then each will be having exactly like frequency divided by k in each of them. Okay, so now if a subarray is awesome, right? If a subarray is awesome, what is a subarray doing? It is fixing the first values of the first multiset, right? It is fixing some values in the first multiset. So if we take a subarray like simply 1, then that will simply just add one element over here, and then we can choose to add the other elements as we see fit. If we want, we can add another one also, and we can do something like this, right? So basically, subarray should add each element, should add elements. This is our third and last observation, less than equal to frequency divided by k times. Okay, so let's say we have 2 2 2 2 2 2 3 3 3 4 4 4, right? So the solution should be 2 2 3 4. Similarly, 2 2 3 4 2 2 3 4. Okay, so that is what the solution should be. But if we had chose a subarray like this, if we chose a subarray, then it would add 2 3 times over here, right? It would add 2 2 2. Now we cannot have 2 2 2 because then we will lose some number of 2's later, right? There will be nothing left here. There will be nothing left here. So that's what is basically the idea. Each element which is being added to the subarray, for it to be awesome, should be less than or equal to the frequency of that element. Okay, so frequency of element in this subarray a of L to R should be less than equal to frequency of that value divided by k for this subarray to be awesome. Subarray to be awesome, and that's the meaning of the word awesome subarray. That's all. This condition is the condition which we need to satisfy. Okay, so I hope this much is understandable, right? Yeah, so each element should have this much. Okay, so now how do we make sure to count the possible LNR for these awesome subarrays? Okay, so let's take an example again, different example, fresh example. So let's say we have 2 3 2 2 4 3 2 um 2 2 3 4 4 and 2. Okay, so as you can see, 2 appears a total of 6 times. 1 2 3 and 1 2 3 6 times. Again, 3 appears a total of 3 times. 4 appears a total of 4 times. Here k is equal to 3. K is equal to 3. So in an optimal bucket, 2 will appear twice, 3 will appear once, and 4 will appear once, right? So in an optimal multiset, this is going to be the answer for that, right? So let's start with our L and R, right? So this will be our L. Let's assume that this position is going to be our L. Okay, then what about R, right? So obviously we can have LNR like this. LNR like this is also valid. LNR like this is also valid, but an LNR like this is not valid, right? Because now we have 3 2's, but we can have at most 2 2's, right? So R can be maximum going up to here. So that gives us 3 possible values of LNR, right? Answer will be increased by 3 because 0 1 2 the possible endpoints for R. So basically 0 0 0 1 and 0 2 are awesome subarrays starting at 0, right? Now what we can do is we can think about starting at 1. So we can think about starting at 1, let's say here, right? And now our L equals 1. So now we have 3 and 2, right? 3 and 2. We can have another 2. Why can we have another 2? Because now there's not a previous 2. So we can have another 2 here, right? We can have another 2 here. We can extend the subarray till here, and we can extend the subarray till here as well, because we have a 3 a 4 and 2 2's, right? Can we extend the subarray even more? No, because now we have through 2 3's in the multiset. So we will stop at this position, and we can say that 1 2 3 4 possible new subarrays are added Basically the subarray is 1 1, 1 2, 1 3, and 1 4. These subarrays are going to be added. Okay, so we can say that answer can be increased by 4 again, right? And so on. We can increase the value of L, and we can find which value of R satisfies this. And this would be an O of n square approach, right? It would be too slow because n goes up to 10 to the power 5, right? N goes up to 10 to the power 5. So here we'll use a concept, a prerequisite concept for this, which is two pointers technique. Okay, concept which is two pointers technique, two pointers. And basically the idea is R will never get smaller. Okay, R will never get smaller. R will always get bigger, because since L at a particular point is going either staying the same or going to the next step, R will also either stay the same or go higher, because we know that if this much is awesome, then this much will also be awesome, right? So R will always stay the same or go higher. So that's why the pointer of L is going once through the array. Similarly, the pointer of R is also going once through the array. Okay. So the amortized time complexity for this will be big O of n, right? The amortized time complexity will be big O of n to do this process using two pointers. Okay. So the solution here is um, do two pointers on L and R, on LR. So what we're going to do is basically, this is the idea. We're going to set answer equals 0. We're going to set R equals 0. Now for each value of L from 0, L is less than N, L plus plus, right? Now we will extend the value of R as much as possible. So while L to R is awesome, do R plus plus, right? Or while L to R plus 1 is awesome, do R plus plus, correct? And then answer will be increased by R minus L plus 1. Okay, so that's the number of values, right? So this is R, this is L. So the number of values in between equals R minus L plus 1, right? So let's say this is position 0, 1, 2, 3, 4. So 4 minus 1 is 3. 4 minus 1 equals 3 plus 1. So these are the total number of subarrays which we have formed, right? 4 subarrays in this case, right? 4 subarrays total. And then once the final, this whole loop finishes, we can print the answer. Okay, print the answer. Now how will we keep checking it is awesome? We simply need to check if the frequency of this element, frequency of, we can maintain a frequency map. So frequency over here, frequency map, or let's just call it map. It can be unordered map or ordered map. Now if we add this value, map of value at R gets added if this remains less than the frequency of this value divided by k, right? So we need to know the frequency of this value divided by k. As long as it remains less than or equal to that, we can keep adding it, right? And when we go to the next step, we need to do map of v of L minus minus to remove the value at the index L from the map. So that's all. It's a sliding window slash two pointers approach. Sliding window slash two pointers approach. uh, the time complexity for it is big O of n if you use unordered map, if you use unordered map, or big O of n log n with a normal map to store the frequencies. Okay, let's have a quick look at the code. So I use a normal map, so it will be n log n. Initially I take in n and k. I find the frequency of all the elements of the original array first. I ensure that all the frequency is divisible by k. If it's not divisible by k, I set the possible value to false and I return 0. I continue. Okay, I print 0 and I continue. Now all the values are divisible by k, and I have a new map called mp. So the old map was the frequency map called frequency. This new map is called mp, right? My r value I've set to -1 over here, so that's fine. You'll see the code, two pointer code. And my initial answer is 0. For each value of L pointer, I will extend my r pointer. So while r is less than n minus 1, I will check if the adding this new value to the map remains less than frequency divided by k. If that is true, then I'll add this new value and do r plus plus. Otherwise, I can break. So now my r has extended to the maximum long value. I can add r plus l plus 1 to my answer. Then to move to the next step, I can remove this value from the map and print the answer. So that's all. A simple two pointer approach. I'm making sure to extend my sliding window up till the point the subarray is awesome. And we are doing this by keeping a frequency map and a normal map and checking if the current number of elements does not exceed the required number of elements in the multiset. Okay, so that's about it. We just need to pay attention to these observations that each value can be at most frequency by k times. So we're just extending it until the value remains until frequency by k. Okay, that's it. And we're using maps to lower the time complexity. So yeah, it's a common two pointer technique question. Yes, it's not a pattern exactly. It's just two pointers. Yeah, it is sliding window or two pointers. Yes. Any doubts on this? You can ask now. Why less than? Because any extra values you can add later, right? That's why we're ensuring that if the map value is less than the frequency value. So while it is less than equal to, we can do it. And yeah, to answer your question, it is a bit of a standard question. Okay. All right. Now we'll move on to problem F. I'll just take a quick break. I need to refill my water bottle. And then we'll quickly get into problem F and problem G. All right. Take a quick break of 2 minutes. Alright, everyone, I'm back. We'll now move on to problem F and G. Um, yeah, I did solve all the problems. You can just pull up the standings and see. Yeah, it's solved in like an hour and a half ish. Okay, are there any questions up till E? Okay, fine. Let's move on to problem F. Um, yeah. Right, so I think finally a bit of a slightly harder problem start here. Okay, so Farmer John has n arrays that may have different lengths. He will stack the arrays on top of each other, resulting in a grid of n rows. The arrays are left aligned and can be stacked in any order he desires. Fine. So let's just take this last test case example. 3, 4, 4, 9, 7, 7. This. So there are three arrays, and the first array is size 3 and it has values 4, 4, 9. Second array is size 7, it has these values. Size 4 it has these values. Okay. So he stacks them in some order. So as you can see, it's some order they have been stacked in. Then gravity will take place. Okay, then gravity will take place. Any cell which is not in bottom row and it does not have an element will beneath it does not have an element beneath it, it will fall down. This process will repeat until there is no cell which can fall, right? So basically it's just going to fall down naturally as if it's like normal gravity, right? And over all the possible ways Farmer John can stack the arrays, output the minimum bottom row after gravity takes place. Okay, on the output the minimum bottom row till gravity takes place. Fine. So basically we need to find lexicographically minimal, or if you don't know what lexicographically minimal is, it means dictionary order minimal last row. Okay, so how do we do this? And here we need to be very careful about the time complexity, because n goes up to 10 power 5, k also goes up to 10 power 5. So k is the size of some individual array, but our best part is that sum of k over all test cases does not exceed 2 times 10 power 5. Okay, so this is a most important constraint which makes the problem doable. Okay, so problem F, we have some arrays and we stack them, and since gravity happens we have some final array which looks like this, and we want this to be lexicographically minimal. Okay, lexicographically minimal. And we also want that if each array has a size of ki, so this array has size k1, k2, k3, right? So we are given that sum of all ki is less than equal to 2 to the power 2 times 10, 2 times 10 power 5. Okay, so we're given this, right? And that means that we have the we have um, time to iterate over all elements in like big O of sum of k of I, or big O of sum of k of I log k of log sum of k of I. Okay, so this is the expected answer. So let's just simplify, write n as capital N as sum of k of I. Then we have basically big O of n log n time at most to find the answer. Okay, so we cannot do n squared solutions, we can't compare two arrays directly, we must find some clever way to do it in this. Okay, so we can visit each element at most once or twice amount of times. Fine. And I think that's the main problem here. It's to figure out how to do this within the correct time complexity. Okay, let's see. So the first thing you observe over here is, let's say our arrays are something like, let's just make some arrays. Okay, so we have the array 1 2, we have the array 1 2 3, we have the array 1 2, maybe we have the array 2 2 2, and then we have the array 3 2 1. Okay, so given this test case, what would be the optimal way to stack them, and the correct way would, what would be the answer? Okay, so the correct answer would be 1 2 1. Okay, the correct answer would be 1 2 1, because we could have something like, right, let's change it to this. Okay, so we could have something like this one at the bottommost, right, 1 2 at the bottommost, and then on top of that 3 to 1. Okay, on top of that 3 to 1, right, and then the answer would be 1 2. This would fall down and it would give us a 1, right? So basically what is happening is, we need to choose in our final answer. So let's say our final answer is, something like this, right, array like this. In this final answer, the first portion can be some array, the first portion can be some array, and this should be lexicographically smallest, lexicographically smallest. And now when this one ends, when this one ends and this next portion starts from some other array, this should also be lexicographically smallest, lexicographically smallest. And then when the next portion starts, this should also be lexicographically smallest, right? So I hope that's understandable, right? And then what we cannot do is, we cannot, for example, for each value we cannot go through this, and then for the next value we go through this, right? I mean, technically we can do that, but we need to somehow keep track of, like in this case where 1 is also there in both cases, should we choose 1 2, this one with 1 2 3, or let's say there was one with 1 2 4. So we'd have to keep track of previous values as well. So it gets a bit complicated on how to iterate through this, right? And mostly the question is not about getting much ideas about how to solve. The question is more about how to implement. Okay, the question is more about how to implement. It's less about how to find a clever solution. The solution is obviously not that hard, right? We need the first portion to be lexicographically smallest, next portion to be lexicographically smallest, next portion to be lexicographically smallest. The main problem is how to implement this. How to solve is obviously, not that hard, right? So first let's just discuss what the optimal solution looks like. So what would optimal solution look like? Okay, so we're given some arrays. Let's say this is the first one. Okay, then this is the second one, and then this is the third one, f4. Okay, so this is a solution with a very high time complexity, but it is a solution. So to help understand what's going on, so in these three, in the arrays which we have, so in the arrays, choose the lexicographically smallest one, choose lexicographically smallest one. Okay, because the first portion must be lexicographically smallest. Choose the lexicographically smallest one. That one we will stack in the bottom. Okay, stack that one in the bottom, stack that one in the bottom. Okay, so imagine this one was lexicographically smallest, then we will stack this in the bottom. We will have this a1 a2 a3 a4 in the bottom. Now on top of that, which one will go? So basically up to a4 we have already stacked, right? So we should only compare from the point a5 onwards. So if there were more arrays, let's say there was another array with an a5, and maybe some array with a5 a6 as well, right? So we need to compare from this point onwards which one is lexicographically smaller, and then from this portion we need to stack the next one, right? So from a5 a6, whichever is lexicographically smaller, that one we need to stack, and so on. Deepraj Singh, don't spam. uh, I got what you're saying, but that won't work, right? Because um, you can't simply find the lexicographically smaller and put int max on them, because then if you just sort the arrays, they would start by comparing the first elements, right? But once you have fixed your first array, then you have to compare the later elements. So let me just give an example, a bigger example. Let's say we have 1 2 3, 1 2 3, 1 2 4, 1 2 5, 1 2 6, 1 2 7. Okay, and then we have this array ends. Okay, and then let's say 7 8 9, 4 2 5, and 4 3 1, 6 3 2, and 5 2 2 5. Okay, so let's say these are our arrays. So the correct way of stacking would be, first we stack this, then we stack this, and then finally we stack this. As you can see, it is not lexicographic order, so this will be 1 2 and 3. It's not simply sorted order. It's so when we stack 1 2 3, that's because we're comparing from the start, right? We're comparing from the start. First we're comparing this first character. Okay, smallest is 1 in all of them. Second character, smallest is 2. Third character, smallest is 3, right? Smallest is 3. So this one, this is the array, we stack this. Okay, now we can cut off all these elements. We can cut off all these elements because these are now useless. Now we only need to compute from this point. Now here smallest can be this one or this one, 4, right? But both of these are equal, so which one should we choose? We check the next element. Here 2 is smaller than 3, so obviously this one we have to stack. So now we can stack 4 to 5, 4 to 5, and now we can again cut off from this point. We can cut off from this point. Now we need to stack the remaining. We can compare 2 5 with 5 2. Obviously 2 5 is smaller, so we can stack 2 5. So our final answer would be 1 2 3, 4 2 5, 2 5, right? This is what we'd be printing. So I hope how the answer is being formed is understood, right? Did you understand, Deepraj? And others, you can put in the chat if there's anything confusing about this, right? So simply the original sorting won't work. We need to, like, if you want to implement this, you'd have to repeatedly sort, but then that would take too much time complexity. Like, delete the part which is already done, sort again, delete the part which is already done, sort again, and that will take too long. That will take n square log n, or maybe higher. Okay, so how do we do this in lesser time complexity, right? And how do we make sure that there's only n log n or big of n time taken? So the way I did this was, and this may not be the best way, but this is the way which I did this, was that first, we will have empty slots for the answer, and this will be of size m. Okay, so the answer will be of size m. M is the max of ki. Okay, so m is equal to max of ki, so max of all the subarrays, oh sorry, max of all the arrays, right? Now what we're going to do is, we'll iterate through each array one by one, and then we are going to put it over here. So let's say the first array was 1 2 3, right? So we put the values 1 2 3 over here, right? Now we compare with the next array. We see that one by one we'll go through the values and we'll compare here 1, here 2, here 4. So obviously it's not better, so we'll leave 1 to 3 as it is. Similarly, we'll try 1 to 5, 1 to 6, 1 to 7. None of them is better, so we'll leave it as it is. Okay. Now we can try the second portion. Now we'll try the second portion. First, we'll put 7, 8, 9 over here. Okay, we'll put 7, 8, 9 over here. 7, 8, 9, 2, 5, let's say. Okay, we put the second portion, which is 7, 8, 9, 2, 5. Now we will try this next array, which is 4 to 5. So we try putting 4 to 5 and we'll compare this portion over here. We'll try 4 to 5 over here. And we will see that 4 is smaller than 7. So yeah, we can put 4 to 5 over here. Okay. We'll put 4 to 5 over here. Now we go to the third array. We try 4, 3, 1. 4, 3, 1. But 3 is smaller than 3 is larger than 2. So we don't replace. Similarly, we try 6, 3, 2. And we don't replace. Okay. And basically what happened is now we got our final answer for this test case. Okay, so the idea is basically the idea is basically we need to keep track of what parts we can insert in. Okay, so we need to put make a answer array make an answer array with all empty values, or you can use infinity values, all empty infinity values for each array. Try to substitute try to substitute the values of the array the values of the array the values of the array in the available positions in the available positions if it is smaller. Okay, if it is smaller, and we need to keep track of each chunk, like where each chunk begins and where each chunk ends. Like here, as you can see, the yellow part is a chunk from subarray 1, right? Similarly, the pink part is a chunk from array 2, the orange part is a chunk from array 3, and something like that, right? So we cannot start editing in the middle of a chunk. We can only start editing from the start of a chunk till the next chunk starts, right? So we need to keep track of that. So with some more examples, I'll make this a bit clear. Let's say our example is, let's say, 1 5 4 2 7 3. Okay, and the next one is 2 2 3 1 3 4 5 1 2 3 4 1 2 3, something like this. Okay, and also one more thing, we are going to process the arrays in increasing order of size. Okay, in increasing order of size. Okay, because we don't want larger arrays to come after, we don't want larger arrays to come before smaller arrays. So we're going to sort them by increasing order of size. Okay, so when we sort them by increasing order of size, what happens? So let's sort them by increasing order of size, and then we get 2 to 3. This has a size of 3. We then have 1 2 3. Then we have 1 3 4 5, 1 2 3 4, and 1 5 4 2 7 3, 4 2 7 3. Okay, now our answer is going to be set to 6 empty values, so 6 values of infinity. Okay, and right now there will be only one chunk, so our chunk starts at this position. So every point our chunk starts at, we can like mark it. So let's say our chunk starts at this position. Okay, so we get the first array, which is 2 to 3. We compare over here. 2 is smaller than infinity, so we can set this value of this array into this. So we can set 2 2 3, infinity infinity infinity. Okay, now the next array we see is 1 2 3, right? 1 2 3. Now the chunk right now is going to be over here. Okay, so one chunk starts here, the next chunk starts here. Okay, so now we're going to compare 1 to 3, and we see that okay, 1 is smaller than 2, 1 is smaller than 2. So we can put it as 1 2 3. We replace this chunk, and we have infinity infinity infinity. And again the starting points of the chunks should be noted, so this chunk and this chunk. Okay, so I call this the editing positions or the chunk positions. So we cannot edit in the middle, right? Because when we have put the 1 2 3 array, we can't start editing over here, we can only start editing from here. So this is the edit or chunk positions. Fine, now we have 1 3 4 5. Okay, so one position to start editing is 1 3 4 5, but here we cannot start editing because 3 is larger than 2, so it's better to just keep the old value, right? So we will not edit from here. What if we start editing from here? So again we had 1 3 4 5, and here we can see 5 is lesser than infinity, so yeah, we can add it over here. And so we will have a new chunk. So 1 2 3 5, infinity infinity. Okay, and now the chunks are going to be, this is the first chunk, this is the second chunk, and then this is the last chunk. The way we can write this is, this is one edit position, this is one edit position, and this is one editable position. Okay, so this is all happening on one array, and each element is being visited exactly once to ensure that the time complexity is within bounds. Okay, so now we have visited this one, we're going to visit the next array, 1 2 3 4. So here when we compare, um, we see that 1 2 3 5, infinity infinity, right? And we'll compare 1 2 3 4 to 1 2 3. So we have 1 2 3 4. We see that this is equal, this is equal, and this is equal, right? Now we are only comparing for the chunk, so this is equal, so we don't need to do anything. We will not do any replacement, right? We will not do any replacement. This chunk is perfectly fine. Now we compare from this chunk. We have 4 versus 5. So since 4 is smaller, we can replace 4 over here. So we can replace it as 4. And now these are our chunks. Fine. So this is an edit position, this is an edit position, and this is an edit position. Now coming to the last array. We will compare its values. So first we'll try the values over here. So 1 5 1 5 and 4. This is larger, so we will not replace. Now we have 2. Okay, so we'll compare 2 with this 4. We see that 2 is a better value than 4, so we'll replace this chunk over here with 2, and then the chunks values will be added, so 7 and 3 will also be added. Okay, and then we have reached the end, there are no more arrays left. We can simply return the current answer, and these are the two chunks, so 1 2 3 and 2 7 3 as our final answer. Fine. So yeah, the implementation was pretty tricky. The main idea is any way you can implement such that each element is visited once, that way will be correct. And the way I did it was by sorting first by the increasing order of size. Okay, so that way the smaller chunks will be considered first, right? They won't interfere with larger chunks, won't interfere with it. Then I will note down where each chunk starts, right? And we can have ensure that we don't start editing in the middle. Then we will compare whether this chunk is better or worse than the current position's value. We'll add it if it's better, otherwise we'll leave it untouched, and then compare the next chunk with the current position's values. That will make sure that only big O of n operations are undertaken, and also that we get the correct answer. Fine, let's have a look at the code. And yeah, it is very important to do this in increasing order of size. All right, let's have a look at the code. All right, so first, um, let me just zoom in case it's small on some screens. Okay, so for each test case, we take in n, and we take in the vector of v, right? So I'm simply taking in for each vector in this, I'm taking the size of the vector k, I'm resizing by that, and then I'm taking each value in that v of I. Okay, so this is just taking input. Now I'm going to sort all these vectors by the size of the vector. Okay, so this is not sorting the vector itself, I'm sorting by size. Okay, so this time complexity of this is just big O of number of vectors, so that's n log n. Okay, so that's just n log n. Um, and let us say sum of all k, we'll call it big O of capital N. Okay, so capital N is equal to sum of all k, sum of all ki. Fine. Small n is equal to the small n which is in the input. Fine. Okay. M is going to be the size of the largest element, the size of the largest element in the vector. Why do we need the largest element of the vector? Um, Largest element of the vector, why do we need the size? Because that will define the final size of the answer, right? So like in this case you have 1 2 3 4 5 6 7, right? So this has three values, this has 7 values, and this has 4 values. So obviously the final answer should have 7 values, right? Also unique asks, after you figured out what to do, did you just start coding, figured out while coding, or were you having a rough idea for it already? So to be honest, no. I First of all, it took me a while to get this idea. If you see, this was the question which I found hardest in the contest, almost 30 to 40 minutes, and I even got one wrong answer on it. So yeah, it was not that obvious, right? It took a bit of time to notice um, how to do it. So yeah, I was not having a rough idea for it already. It took some time to figure out how to save the time complexity, and I tried some ways to figure it out. All right. So yeah, now I'm taking the size of the last element. Initially, all my answer is set to 10th power 9 because that's infinity, right? Roughly infinity for my purpose. Um, Also the edit value. So the edit positions are set to 0. Okay. So that means that these are the positions where I can do edits in, or these are the positions where my chunks will start. Okay. So now for each value, for each vector in my list of vectors, k is the size of the vector for each chunk. So in each chunk means edit dot size, right? So edit each possible value where I can edit. I will find my L and R. So L is basically the start of the chunk, R is the end of the chunk. Okay. So over here L will be like this. So L will be this, R will be this. Okay. Similarly, this will be L and this will be R for the next chunk. Okay. Or if you look at this subcase, then this is one L and this is one R, and then again this is one L and this is one R itself, and then this is one L and this is one R. So I'm comparing all these chunks which I have formed. Um, Now for each chunk, I want to know whether I have to replace or not. Initially, replace is set to false. Okay. So I go through everything from L to R in this chunk. If this vector is worse than the answer, then I can just break. If this vector is better than the answer, then I can set replace equals true and then break. Now if replace is equal true, that means that I'm replacing this chunk. And so basically from L all the way to K, I have replaced with this chunk. So while that is true, I'll replace this chunk. So ans of I equals v of I, and then I need to make sure that the edit positions are correct. So I can delete all the other values of edit position and push back the k value, right? And then I can continue this until all the vectors are processed. Finally, I can print my answer array. So if you're having any doubts with this, just go through the code a few times. You'll get it. It's in my opinion, the code is pretty clean. Basically, for each chunk, we're just taking the lnr value of the chunk, and we're checking if we can replace that chunk or not. Does that improve it or not? If it can replace, we replace it and we fix the values of the chunks again, right? And the overall time complexity is n log n plus n, big N, and big N is basically the sum of all ki, right? So that's, I think, the main thing which matters. So we can just write it like big N itself. So the final time complexity for this would be um, big O of n log n plus sum of all ki. So it's final time complexity. All right, that's all for this problem. Any doubts, please ask. Although I do understand that if understanding the implementation like this would be a bit confusing, take a pen and paper and go through the code. Maybe after the video, rewatch this section. It will become clear. Okay. So moving on to problem G, unless anyone has some major doubt with F, we can move on to problem G. To be honest, for me, problem G was easier than F. So maybe if people were struggling with F, you could have gone for G. At least the implementation is easier. Okay, let us go ahead and read problem G. Farmer John's last wish. Um, Bessie found an array A of length and on the floor. Uh, it basically says let f of a denote maximum integer k in the range of 1 to n, such that GCD of a of 1 to a of k is greater than GCD of a of 1 to a of k plus 1, or 0 if no such k exists. Um, G of a is the maximum value of f of a over all possible orderings of a. Bessie decides not only to find G of a, but also the value of G of p for all prefixes p of a. Output n integers, the ith of which is g of a1, a2, ai, right? So for all prefixes, we need to find g of a, g of that prefix, n again goes up to 10 power 5, and yeah, that's about the time complexity. So the time complexity should be n, n log n, n root n, something like that, right? Problem G. We can write the expected time complexity already. So expected time complexity, it can be big O of n, big O of n log n, n root n, something like this. Okay, so let us simplify the problem. So we need a point such that GCD of a to k is greater than GCD of a to k plus 1, right? So that basically means that and we can rearrange this, we can rearrange, and we need to find the maximum such point. Okay, so let's take some array. Let's say this array 2 4 3 6 5 7 8 6. 2 4 3 6 5 7 8 6, right? Now the GCD of this whole array, GCD of the whole array is obviously equal to 1, right? We know that the GCD of this whole array will be equal to 1. You can check that if you want, but we want to find the largest prefix such that the GCD is greater than the next possible GCD, right? So basically, we need to find the prefix GCDs. We need to find an ordering of this, such that such that GCD remains greater than 1 for as long as possible. For as long as possible. Okay, we need the reordering of this so that the GCD remains greater than 1 for as long as possible. And what does that mean? Basically, we need a common factor. We need a common factor for the prefix. Okay, for the prefix as long as possible. As long as possible. So we need to choose some number which can be a common factor for our prefix for as long as possible. And one way we can do that is choose all the even numbers. Okay, so 1, 2, 3, 4, 5. Right, there are 5 even numbers. So if we put them in the front, 2, 4, 6, 8, 6, then the other remaining odd numbers like 3, 5, and 7. 3, 5, and 7. Then we'll have a prefix of size 5, right? Prefix of size 5 whose GCD is equal to 2, and this one's GCD is equal to 1 over here. So basically there's a common factor of 2 as long as possible. So our answer is equal to 5, right? Our answer is equal to 5, and that's what's the answer for this prefix. Now we need to find this answer for every possible prefix as well, right? What is the rating of F? Yeah, maybe 1400, 1500. That is a good estimate, I think. And for G also maybe about 1500, 1600 max. 15 to 1600 I would say for F and G. Okay, so how do we ensure to have a common factor in the prefix for as long as possible? And yeah, so one thing we can note is, um, let's say we have a bunch of numbers. Let's take my own custom example. Fine, let's take a known example. Let's say I have a bunch of numbers like, okay, first let's take an example where everything is equal. Okay, like fours, only 4, right? Now here the answer will be 0, because simply the whole GCD itself is never changing. The GCD will be 4 here, 4 here, 4 here, right? The GCD array, let's make a GCD array. It will be 4, 4, 4, 4. GCD never changes, so the answer is always 0. The answer is always 0. Okay, now let's say we added some other value like 2, 2 to 1. Okay, so the GCD changes from 4, 4, 4, 4 to 2 to 2 to 1, right? um, Even if this value was 3 over here, then still it would be like this itself, right? So we can say that, um, let's say we are at this point of the array, our answer will still now be 0. But as soon as we move to this point, because the GCD changed here, right? The prefix GCD changed at this point. Prefix GCD changed at this point, changed here. Our answer is going to be 1, 2, 3, 4. Why? Because this point had some prefix GCD, and this point has a different prefix GCD. That means these had some common factors, right? There was a change which occurred here. So the answer over here will be 4. Now if we go on to here, the answer is also going to remain 4. And here again there's a change in the DCD, and the answer will be 6. Okay, so this is how the answer for this test case will be formed. Okay, so basically what have we observed? um, so observation 1, if all values in prefix 0 to I, right, the prefix from 0 to I are the same, then answer of I is equal to 0. Okay, if they are the same, then it's equal to 0. If GCD from 0 to I minus 1 is not equal to GCD from 0 to I, right? Prefix GCD basically. Then answer is equal to I. Okay, because all the elements had some common thing. Now the new element does not have that in common factor. So answer is equal to I. So these are the two observations we can make from that example. Okay. The first example is first observation is obvious. Second observation might be that clear. So please understand it. Basically, I'm saying if the GCD has changed at this point, that means that obviously the maximum prefix, the maximum value of over all reorderings will simply be I itself, right? Because if the GCD changed after I elements, when you added the I plus one element, then the answer of I should be I. Okay. So is that clear, guys? Also, Unique, what exactly are you asking? I didn't quite get your question. You can ask it again, maybe ask it an example, so I'll answer it. This diff4 was rated? Yeah, it's rated for people whose rating is below 1400. This is for Supriya. It is rated, yes. At least as far as I know, last I saw. Yeah, rated is there. As long as you registered as rated, it would be rated. Okay. So these two observations we have down. These are basic observations. Now, what about more complicated cases? Okay. So, for example, let's take an array like this. Um, 10, 10, 2, 2, 2, 5, 5, 5, 5, 3, 3. Okay. So if we take a prefix in this, let's just find the answers for these. Okay. So the answer initially will be 0 because this is our array and that's not much. That's only one element. And then here also all the values are equal. So again, the answer is 0. Now here the GCD will change. The prefix GCD will change. It was 10, 10. It became 2 now. So that's why the answer is going to be 1, 2. Right. So the answer is 2. Now for this test case, you want to find the answer, and I'll just tell you that the answer is 2. We'll explain why later. So the answer is 2. The answer is 2 here as well. Okay. So now when we get the 5, right, our GCD has become 1. So our answer can be 1, 2, 3, 4, 5. Okay, the answer can be 1, 2, 3, 4, 5. Right. Which is answer of I equals I. Right. Now here what will be the answer? Here the answer will basically be in this subarray, what is the maximum common factors which we can find, which is the common factor such that the maximum elements we can put in the prefix. Okay, so the maximum elements of this common factor we can put in the prefix. So basically GCD of this whole thing is 1 right now, right? Um, GCD of 2 comma 5 is 1. So basically GCD of this subarray is 1. GCD of this subarray is equal to 1, right? So we want to make it such that this GCD becomes equal to 1 at the last possible point. Okay, at the last possible point, what arrangement will make that possible? And the current arrangement in fact works, and that is giving us 5, because we can have this is divisible by 2, divisible by 2, divisible by 2, divisible by 2, divisible by 2. So only here the values are not divisible by 2. So that's why this works, and we can write 5, right? But moving on, will it still work? So let's say we are at this point of the array. Okay, this point. Now what happens is, um, if we take divisible by 2, then they are exactly 5 values divisible by 2. But if we take divisible by 5, they are 1, 2, 3, 4, 5, 6. 6 values which are divisible by 5. Okay, there are 6 values which are divisible by 5. So basically, if we rearrange this array to be something like this: 10, 10, 5, 5, 5, 5, 2, 2. If we could rearrange this prefix like this, okay, then what would happen is we would have these 6 values, okay, they will have GCD of 5, right? These will have 6 GCD of 5, and then finally the GCD would become 1 over here. So the last point of change, would be at 6. Okay, the last point of change would be at 6. So basically we're ensuring that we have the longest chain of values which are divisible by the same number. So here it's divisible by 5, right? So our answer here would be 6. Okay, the answer here would be 6. Similarly, the answer remains 6 for the rest of the values. And this is the answer for the test case. Okay, this is the answer for this example. So basically, in the old two cases hold. So after observation 1 and observation 2, observation 3 is for if both the cases did not work. So then our answer can be equal to maximum of answer minus 1. Okay, and the other value is the value with, or maybe we can say, frequency of numbers, highest frequency of numbers with a particular divisor, with a particular divisor. Okay, and this divisor should be greater than the GCD. Okay, this divisor should be greater than the GCD. It cannot be equal to the GCD, because then there is no change happening, right? Here we need a change to happen, like from 5 to 1 the GCD becomes. So we can't just say 1 is the divisor which divides everything, because that is not valid, right? We need some divisor greater than the GCD. Okay, so basically our answer at each position, answer at each prefix I is equal to the frequency of numbers with a divisor, with a divisor greater than the GCD, maximum of the frequency of numbers with a great divisor greater than the GCD. Okay, because we will put them in the start and then the remaining numbers in the end, and that would maximize our answer at every prefix value. Okay, so now how do we keep track of this? uh, how to implement this, right? How to implement this? And the way we'll do this is by simply right, so the way we can do this is make one last observation, observation 4, either the new element, either the new element added to the prefix. So as we do the prefix from left to right, um, added to the prefix changes the answer or not. Okay, changes the answer or not. Okay, so or not, so a kind of DP of sorts. So either the new element added to the prefix changes the answer to or not. So if it does not change the answer, then the answer remains the previous answer itself. So answer will remain answer of I minus 1, or it will be affected by one of the divisors of this new number. Okay, so number of occurrences or frequency of some value of divisors of the new number, of divisors of A of I. Okay, divisor which is greater than GCD, right? So that's all. We need to find these two values, and what we can do is we can make a map for each divisor, for each divisor we can have number of occurrence. Then we can simply check if we store this in a map in a given prefix, in a given prefix, in a given prefix. So if we store this in a map, store the divisors of all numbers, of all numbers in the map, in the map, then we can simply check the maximum one, the maximum frequency divisor greater than GCD. Okay, greater than GCD. So that's the basic idea. um, One thing to keep note is how to find divisors. So I hope you know how to find divisors. How to find divisors, we need to do this in optimized fashion. So the way we need to do this is big O of root n. So basically we just need to check all the numbers from I equals 1 to I equals root n, and a divisor is either I or x divided by I, right? For some given number x, the divisor can be I or x divided by I. So we can find all the divisors of a number in big O of root n. So the time complexity for this will be big O of root n, n root n log n. So if we use a map, it will be n root n log n. If we use an unordered map, it will be big O of n root n. Okay. So basically the algorithm, we'll write the final algorithm down. Um, Let me just write the final algorithm. Final algo, and answer at position 0 will simply be 0. Okay. And we will keep track of prefix GCD. So for I equals 1 to I equals n minus 1, add divisors of A of I to the map. Okay, to the map. And if prefix GCD, prefix at I is not equal to is not equal to prefix of I minus 1, then the answer is simply equal to I. So answer of I is equal to I. Otherwise, else answer of I can either remain the same. So answer of I will be the max of remaining the same, or it can be the value, the divisor with the maximum occurrences, right? So for all divisors of I, we can do a check. So for all divisor of A of I, maximum frequency divisor in the prefix. Okay, right. So since we have already added all of these divisors to the map, we just need to check for each divisor of A of I which has the maximum frequency in the map. So basically this is big O of n, big O of root n, and this is big O of n. So if we multiply them, we get n root n. Similarly, this thing to check all the divisors again is big O of root n, right? If you use a normal map, it will add an extra log n factor. But since we're using unordered map, it will simply be big O of n root n, right? And then finally, once this is done, we can simply print the answer array. Print answer. The overall time complexity for this approach is big O of n root n. Okay. Let's have a quick look at the code, which would clear most of this up. Okay. So in the start, just keep in mind we have an unordered map for divisors. For each divisor, it will have the frequency of that divisor occurring till so far. Okay. We take in n, we take in the vector, we clear the divisor because it's being stored as a global array for convenience, global map for convenience. That's why you have to clear it before using it. Our answer is set to all zeros. We are calculating a prefix GCD so far. So instead of having an array, we just need the current prefix GCD, right? So we're calculating it manually. We're also adding the divisors to div for v of 0. Okay. So I made a helper function called add divisor. Basically what it does is it goes through all the divisors. If the divisor is there, like if for each divisor, it's adding it to the count of divisors. Okay. So if it occurs, then it gets added to the count of divisors. Now for each I from 1 to n, we added two divisors. If the prefix GCD gets updated, if the prefix GCD is not the same as the GCD of prefix and v of I, then our answer is simply equal to I, right? So this is the first case which we are handling, observation 2. Now otherwise else case, either the answer remains the same. So answer is the same as I minus 1, or it is the divisor which the maximum count, which is a divisor of v of I and also greater than prefix GCD. So here I have a helper function max count divisor. It checks for each divisor. So divisor should be, yeah, so divisor should have GCD in it, and it should be greater than GCD. If the it takes the maximum count of this, so max of m and divisor count I, right? So divisor divs has the number of frequencies, so it's taking max of m and divs. So m is this temporary variable, max of m and divs. Similarly for x divided by I, and yeah, is returning m, which is the divisor with maximum count. Okay, so that's why answer of I equals max of answer of I minus 1, and this maximum count of device, maximum frequently occurring divisor. Now we simply update the prefix GCD, and at the very end we print the answer array. So the overall time complexity for this is big of n root n, big of n to go through the array, and to add divisor and also check the divisor count, it is root n, because they can be up to root n divisors. All right. So yeah, that's about the idea for this. Can I explain the thought process behind this? Repeating cases. I did not quite understand what you mean by repeating cases, Lavanya. Can you please explain that? Raghav will, if you want to discuss E, we'll get to it at the end of this. First, we'll finish problem G. At the end, I'll take general doubts and I can revisit your old doubts. How to use Carrot? Just Google Carrot extension and download. Repeating values. I didn't quite understand what you mean by repeating values. Do you mean answer phi equals answer phi minus 1? Uh, I'm not understanding what you mean exactly by repeating values. Can you please put that on chat? Okay, so main idea over here is, um, if your prefix GCD changed, so this was our observation 2, right? So if your prefix GCD changed, then it's very simple to know that simple answer of I will be equal to I. So if you understood this part, you can, I hope you understood this part. Now, if your prefix GCD was not changing, that was our third observation. If your prefix GCD was not changing, um, third and fourth observations was basically, yeah, we need to find the maximum frequent divisor. Okay, so we need to find the divisor. We need to find the divisor in the prefix values, in the prefix elements, such that maximum of those maximum frequency of those elements are divided by this divisor, are divisible by it. Okay, by it. So this, and whatever the count of that is, that would be the answer. uh, right? So basically what I'm saying is, let's take an example. Okay, we'll take an example and we'll do the array itself. So let's say we have this test case itself, which we were discussing earlier. Okay, let's say we have 10, 10, 2, 2, 5, 5, 5, 3. Okay, so now initially the first value will be 0 always. Now when we go to the second value, yeah, so the first value will be 0 always. And what will our divisor frequency map have basically? Our map divisors will have, so what are the factors of 10? Okay, the factors of 10 are equal to 1, 2, 5, and 10. So now because 10 has been added to the array, we're going to add 1, 2, 5, and 10 in our divisor count. So count of divisor 1 plus plus count of divisor 2 plus plus, count of divisor 5 plus plus, and count of divisor 10 plus plus. Okay, so this is what happens. And so the current counts of divisor 1, 2, and 5, that will be equal to 1 occurs one time, 2 occurs one time, 5 occurs one time, and 10 occurs one time. Now we move on to the next value, and here we see that prefix GCD has not changed, and basically now we will count. Now we will increase the divisors count. Okay, so we will increase the divisors count. Here again, it's 10 again, so 1 now appears 2 times, right? 1 will now appear 2 times as a divisor, 2 will appear 2 times as a divisor, 5 will appear 2 times as a divisor, 10 will appear 2 times as a divisor. Okay, and the GCD so far, prefix GCD so far, GCD is equal to 10, right? Prefix GCD is equal to 10, and we need to look for any divisors over here, any of these, which is greater than 10, right? Which is greater than 10, uh, and we can take the maximum one of that. But there is nothing greater than 10 here, so our answer will again be 0. Okay, our answer again will be 0. Okay, now we go to 10, 10, 2, right? So what are the divisors of 2? 1 is a divisor of 2, right? 1 is a divisor of 2. So we have 3 over here. And similarly, 2 is a divisor of 2. So we have another 3 over here. Okay. So now, when we include the 2 over here, what we're looking for is basically um, any value such that it's such that it occurs such that it's greater than 2, right? So now the GCD is equal to 2. So any value which is greater than 2, any divisor which is greater than 2, and which has maximum frequency. So there are two values which are greater than 2, which is one is 5 and one is 10. Both have frequency of 2. So we can say that the answer over here is 2. All right. Answer over here is 2. Fine. Okay. Now we include another 2. Okay. And now the frequency of 1 and 2 become 4. Right. This will become 4. This will also become 4. Again, we look for a divisor which is greater than 2. So the GCD over here is 2. Any divisor which is greater than 2, which has a higher frequency. So we can say that again only 5 and 10 are there and both have frequency of 2. So our answer for this case is 2. All right. Now we can increase yet more, and now the GCD becomes 1. Okay, the GCD becomes 1. This one's factors need to be counted. So 5 becomes 3 over here, right? 5 becomes 3 and 1 becomes 4. Okay, so the factors are getting added. As you can see, 5 has factors 1 and 5, right? So those factors will get added. So 5 gets added 1 and 1 gets added by 1. Now we need anything greater than GCD. So GCD is 1. So any value greater than this, any value greater than 1 in this divisibility array. So 4 works, 3 works, 2 works. And which is the max out of 4, 2, and 3? Well, 4 is the max. So we will put 4 as our answer. Okay. Now we're going to extend even more. And even here our GCD is 1. This again increases 1 and 5. So this will make it 6. And this will make it 4. Right. Now again greater than 1, any factor we need. And 2 works as a divisibility factor, 5 works as a divisibility factor. And what this basically means is we can rearrange it so that all the factors of 2 are in the start, right? So 2, 2, 10, 10, then 5, 5, right? And that would make this prefix have a GCD of 2. So 4 values would have GCD of 2 and these 2 will have GCD of 1, right? So that is the longest possible way. Or another way here, since 5 also is equal, it could be like 5, 5, 10, 10, then 2, 2. And this would also have 4 as our longest possible value, which would be our answer. Okay, so the answer to this case also is 4. Right. Now again when we extend our subarray, again we'll extend our subarray. GCD is 1, subarray is extended till here. The count of 5 has become 5 now. The count of 5 has become 5. The count of 1 has become 7 now. Now again GCD is 1, so any value of divisible divisor greater than 1 we need with the highest count. Now the highest count is for 5, so our answer here becomes 5. Okay, and so on. And this is the key part, the answer over here becomes 5. Why does it become 5? Because now 5 is occurring 5 times in the array. The 5 has a frequency of 5 times. So 1, 2, 3, 4, 5, all these elements are divisible by 5. So we can write them as 10, 10, 5, 5, 5 if we rearrange like this, and 2 is like this. Then as you can see, these ones have GCD of 5 and this one has GCD of 1 and 1. So our answer will be 5 for this case. Okay, so that's basically the idea. uh, does this clear your doubt, Lavanya? If not, please explain your doubt a bit more. um, why is answer equal to the max frequency of values greater than the current GCD? um, it's simple, right? We want our GCD to change at the last possible point. So basically, read the question again. We want a of 1 to a of k to be like the GCD is changing, right? GCD from a of 1 to ak is greater than GCD of a1 to ak plus 1. So the change point of the GCD should be as max as possible, right? Maximum value of f of a over all possible reorderings of a. So the GCD should change at the last possible point in our array. So for example, let's say we have this prefix, right? We have this prefix like 10, 10, 2, 2, 5, 5, 5. So we have 10, 10, 2, 2, 5, 5, 5. We want the GCD to change at the last possible point. So what happens if we put, let's say, in this ordering, 10, 2, 5, 2, 5, 5, 10. Okay, then what will happen is, let us write the GCDs. Here the GCD is 10, then here the GCD becomes 2, then it becomes 1, 1, 1, 1, and 1, right? And what happens, the GCD changed at the last point at this point. So the answer would be 3 if we just did this kind of an ordering, right? And that's why this ordering is bad, because the GCD is changing very quickly and it's reaching 1, right? But if we rearrange in a way such that it is like, for example, 10, 10, 5, 5, 5, then 2, 2. Then the thing is, these starts all have a common factor of 5, right? These starting values have a common factor of 5. So the GCD would be like 10, 10, 5, 5, 5, 1, 1, right? So the last point that the GCD changed was over here, right? After 1, 2, 3, 4, 5 moves, the GCD changed over here. So that's why this is the best possible arrangement. And the way we are doing this is by putting some common factor of the elements in the start, right? Some common factor of the elements in the start, right? So the GCD is 1. Something greater than 1 should be a common factor in the start. Okay, and that's why we are seeing which of these factors is appearing the most number of times. And we see that 5 is appearing most number of times. It's appearing 5 times. So if we put it in the start, that much later we can make it to change to 1, basically. So that's the idea behind this. Hope this clears it up. Raghav, I'll just get to your question now. Yeah. Okay, so we'll go through the code for this quickly. Um, yeah, so we went through the code, right? I think we went to the code already. Yeah. So just some notes, because I think some people were unclear with this. So yeah, for each value, we are adding its divisors to V of I, right? We're adding its divisors to the divisor frequency map, and then we are updating it. So the new value added is the one which is changing it, right? So either we have the old value itself or the new value which has been added, that is the value which is changing our answer. So that's why we're taking max of the old value versus the um, versus the maximum frequency of the values which have divided it, right? So for all the divisors of the newly added value, we are taking the maximum frequency one. So basically in this array, whatever are the devices, we're taking the maximum frequency one of that, right? So only the new value changes it. So that's why we're only checking for the ones, for the devices of the new value. Okay. Yeah. So that's about it for this question. All right. So the time complexity, as I mentioned, is n root n. Okay. So now we can do all doubts, right? And we can address Raghav's doubt on problem E. Okay. What is rating of E? I don't know. I mean, rating will only be decided weeks after the contest, right? But I can make a guess that E would be about 1200 to 1300, 1300 maybe rating, because two pointers are being used. They already added the tags, I think. Yeah, two pointers. How is subarray awesome? If A L to R is awesome, then how all elements are awesome inside it are awesome, as elements would not be equally distributed in all multisets. I didn't quite understand what you're asking. Let me just, I'll just re-explain E if you want. So basically the idea for E is, um, maybe you might want to rewatch that part as well, because I did spend some time on it. Um, the idea basically is, if your current subarray, if it has less than or equal to the number of elements which appear, right? So for each element, each value which is appearing in this subarray, if it's less than equal to the frequency required of that multiset, right? If it's less than equal to frequency of v divided by k, then it is a awesome subarray. So that was the how all elements in. Oh, okay, okay, okay. You're asking. Oh, you're asking why I'm adding r minus l plus one, right? You're asking this. Why am I adding this, right? This is your question. Okay, so that is very simple. Okay, think about it. If a particular subarray is awesome, then all its subarrays will also be awesome. Okay, I'll show you why. Let's just go to the end. So let's say I have 5 4 3 3 3 4 4 5 5 5 5 5. Okay, so this is my array. Now k equals 3 again. So 3 is a nice example, right? So our optimal set will have something like 5 5 4 3. Similarly, this would have 5 5 4 3, and this would also have 5 5 4 3 in the multisets. Okay, so now let's say if you start at this L, then R would go up to here, right? Our sliding window R would go up to here. Now I'm saying that if this thing is an awesome array, awesome subarray, that means that this also has to be awesome subarray, and this also has to be awesome subarray. Why is that? Not the elements. I'm saying that this subarray, and this subarray are awesome. Okay, so I'm saying that the subarray, the subarray 543 is awesome. 543 is awesome means that 54 is also awesome. 54 is awesome also, and 5 is also awesome. Okay, is also awesome. And reason is that let's say if I add 543, right? If I added 543, then I can add the remaining elements, right? I can add one more 5 over here, and then I can add 5543 here, 5543 here, and I can make all of them equal. Now what if I had only 54, right? What if I had only 54? If I had only 54, then what I would do, then again I can add 3 over here and 5 over here. I can add 5543 and 5543, and I would make all of them equal again, right? And basically, if some array is awesome, then its subarray also is awesome, because you can simply add that yourself, right? You can add that yourself as Farmer John. You can add the extra element yourself. So see, definition of awesome means that, let's go to E. Definition of awesome means that you can place a of I in the subarray. In the subarray, you must place in multiset 1, and the others you can place in any multiset you want, right? So the ones which are in the subarray L are, you have to place in multiset 1, and the others you can place in any multiset you want. Okay, so basically what this means is, um, if a given subarray is awesome, then its smaller subarrays inside it, sub subarrays, they will also be awesome, simply because I'm going to place 543 in the first set, then I can place 54 also, and then I can place 3 in the second process, right? So basically, this is the step 1, that all the A of I get placed in multiset 1. This is the step 2. He can choose anything he wants. So if he wants, he can place the same thing here as well, right? That's what I'm trying to say. Raghav, just do one thing, okay? See the definition of awesome, then try to see if 543 is awesome. Okay, if 543 is awesome, you agree? If 543 is awesome, you can show that, you can prove that, you can prove that 54 is also awesome. Okay, 54 is also awesome. Like, this satisfies the definition of awesome. Awesome just means that I can add some elements so that all the three multisets become equal. Okay, I can add some elements so that all the three multisets can become equal. If for 543 I can do that, that means for 54 also I can do that, right? I hope you're understanding. And why am I adding r minus l plus 1? Because I need to count the number of subarrays, right? um, aim is to aim is to count the number of subarrays that are awesome, that are awesome. So subarray starting at L, subarray starting at L, at L, and ending at R, ending at R, where R is the maximum point that it is still awesome, right? R is maximum point that it is still awesome, maximum point that it is still awesome, it is still awesome. Then that means that all these sub-subarrays should also be counted. So if L to R is counted, then L to R minus 1 should also be counted, L to R minus 2 should be counted, similarly L to L, all of these should be counted, and the total count is R minus L plus 1. That's why, right? Yeah, awesome just means that you can add the other values however you want, so that all the multisets are equal, and that means that the sub-subarrays will also be obviously being counted. And basically it means that the frequencies of each element should be less than or equal to the required frequency. That's it. Overall review, were the problems tricky or tough? To be honest, my opinion would be a bit biased, since obviously I'm a div 2 div 1 competitor. um, for me, most of these problems were pretty straightforward. The only one which I could say was interesting was F, problem F. Other than that, all the other problems were pretty simple to me, straightforward. At least A to D was definitely straightforward. E also was somewhat straightforward. F you could say was tricky because implementation. G was also quite straightforward in my opinion. Yeah, that is fine. Like, if you're completely stuck at some particular problem in a contest, then it's okay to skip. But the thing is, sometimes you should also look at the solve count, right? If the solve count is high, it might mean that you're just missing some small thing, and in that case, if you skip, it might cost you. So yeah, that comes with experience, to learn when to skip or not. I prefer not to skip usually, but if I'm stuck for half an hour, 40 minutes, then I go to the next question. Completely stuck, that is. It's been a long time since there was a div 4, so I'm not even sure what the expected level of a div 4 is. But yeah, the contest was easy-ish. Okay, any other doubts, guys? All right then, guys. Hope you had a good contest. Wish you good rating. I guess that's about it for this session. We have discussed all the problems. Yeah, 6 months back was the last div 4. All right, thank you, guys. Thank you. Definitely check out Eliminator's course if you haven't, right? Like I mentioned. And yeah, thanks for watching and see you next time.